Bismillah wa salatu wassalamu ala Rasulillah. Assalamu alaikum. Hi everyone. Thank you for your attending and special thanks to the people who prepared this conference. Let me introduce myself with a few words. I am Nadim Al-Kilani. I am a Palestinian citizen. I am a PhD student at Rovera I. Virgili University. My field is in the computer vision, specifically in medical image analysis for the breast cancer. I'm so excited to share my topic with you. My topic here, breast ultrasound CAD system based on efficient tumor segmentation network and transfer learned features. So let us go. This is our agenda today. We will talk about introduction, motivation, related work, methodology, experiments, and results. Finally, we will talk about the conclusion and our future work. Breast cancer is the second most common type of the cancer in the world after lung cancer and leading cause of the cancer death among women. In 2020, about 2 million new cases were diagnosed in women across the world, and about 500,000 women died in this disease. So, early detection is the most effective way and method for diagnosing and treating breast cancer, since it increases the likelihood of the treatment effectiveness and survival. Generally, the manual inspection to determine the lesion's benign or malignant status, it is subjective and time-consuming, and it needs a professional doctor to do this task. This motivates us to build an automatic system that can be able to find the tumor in the breast and to decide if it is malignant or benign. Also, to define the location of the tumor, the shape, and which stage it is, in early stages or in the late stages. So we present a deep CNN CAD system for segment and classifying breast tumor. Many researchers put their efforts in this field. So YAB developed survival fully FCN based variants for semantic segmentation for breast in breast ultrasound images. They used a data set of 113 images and 356 for 113 images for malignant and 356 for benign. They obtained a DICE score of 76 with benign lesions and DICE score with 54% with malignant lesions. Al-Majid modified the enhanced unit for lesion segmentation in bus images with contrast enhanced and speckled reduction. They used dataset about 201 bus images and they obtained a DICE score of 83%. So now we will talk about our methodology. We developed a complete CAD system for breast cancer segmentation and classification using modern techniques of deep learning architectures. We built two models, one for segmentation, another for classification task. We trained our model encoder-decoder segmentation network to segment breast tumor. Then we used a best-trained segmentation network to segment bus image. Also, we trained a CNN network to extract texture feature from segmented tumor to classify benign or malignant. This our architecture depicts the proposed CAD system. Firstly, using the segmentation model to automatically localize and segment the breast tumor from bus images. After that, the segmentation mask is multiplied with the input bus image to extract the breast tumor region. Finally, the CAD system uses a deep learning texture extractor to extract texture information from the region of interest to classify the segmented tumor as benign or malignant. Here at the end, the test system, suppose we put it in the hospital, the doctor just insert the image and our system will automatically detect the tumor as shown here, the segmented part. After that, we define the tumor if it is benign or malignant. So as it appears here, we depend on the texture feature. So we will multiply the segmented part with the original picture, the original image, and learn and train our model to in this texture part to finally classify it if it is malignant and or benign. As it will known, the loss function is the backbone and the most important backbone of the deep learning models. In our task, our model, in our cases, the data set is imbalanced. So the background is bigger than the foreground. And we try to find the segmented part from the whole images. So we concerned to train our model with the losses function that play well with the imbalanced data sets. Here is our losses function. We use the standard one, the binary cross entropy and the dice loss. And also we use the loss function that concerned with the imbalanced data set like focal loss and Tversky loss, which has a hyperparameter alpha, beta, and gamma, and we can tune them in order to find the best accuracy. It is worth to mention that we use data augmentation of our dataset because our dataset is just about 163 and we just trained about 113 to model, and we keep about 50 images for the test dataset. Before we check our system before we using the data augmentation, the accuracy in the segmentation part was about 60%. After we use the data augmentation, the accuracy become high. Here's the loss function. We used them binary cross entropy, dice, and we make a fusion loss function. We add binary cross entropy with dice, also focal Tversky. We see that binary cross entropy and dice registered the best accuracy. It achieved about 75% in dice and 67 in CAD. The final experiment for the segmentation part. This is the backbones. We use them: VGG 13, VGG 16, MobileNet, ResNet 18. Also, we use the modern deep learning network, new one like ResNext and Wide ResNet. And Wide ResNet achieved the best one. It registered about 77% in dice and 69% in CAD. Here is after we get the segmented part, we trained the model to learn the this is the sample of the segmentation result. Each model is defined VGG 16, MobileNet, ResNext and the error is shown with these colors. Sign it true positive, and red it means false positive, yellow false negative, and background true negative. Here is the sample of the result in the segment in a classification. So after we trained our model to segmentation part, we took the segmented part and multiply with the original image and trained the model in these texture features, and this is the result. malignant, benign, and so on. And this is the confusion matrix, and ROC in the confusion matrix, the number of the correct and incorrect prediction made by classifier of benign and malignant classes. In case of benign tumors, two predictions are wrong out of 32 images, whereas in the case of the malignant tumors, 5 predictions are wrong out of 18 images. Here is also the ROC curve. It shows the trade-off between sensitivity and specificity. The area under the ROC curve about 83%. As conclusions, we introduced a two-stage CAD system for breast tumor segmentation and classification based on the latest deep learning techniques with a data set of 163 ultrasound images. Our CAD system achieved a DICE score 77% in the segmentation task and an accuracy of 86% in classification task. On the future work, we will employ deep attention mechanisms and metheuristic algorithm like WOA to enhance the performance of the proposed CAD system. Moreover, we will use recent deep learning architectures like ConvNeXt, transformers, and CodeNet. Thank you for your attention, and I'm ready to answer your questions.